So we said this action was something of the form minus a half integral d to sigma, where we agreed to call sigma 0 tau and sigma 1 sigma. And the action ended up being something of the form so something that somebody could have asked, or I could have asked you, was the following. Remember, we started everything by calling these x's phi's, right? And the phi's, we said that they were scalar fields. We said at the beginning of the lecture yesterday, we said, let's study GR coupled to scalar fields, right? Well, that's very good, but that sounds funny because there is an index mu that they have. Does that sound strange? That I'm calling them scalars and then they have this index mu sitting around? Can anyone explain the apparent contradiction?
It's not a contradiction, it's just internal index. It's a set of stars. This index just labels.
Very good, very good. But that index also sounds like, well, in other words, when somebody talks about a tensor, a vector, or a scalar, or anything, just saying that something is a scalar is a meaningless statement, right? Unless they tell you that they are a scalar under a particular transformation, right? So whenever somebody talks about some property of a field, you have to ask, if it's not obvious, under what transformation are you talking about, right? So these x's are scalars under what transformation?
The coordinate transformation of sigma.
Very good. Under transformations on what is called the world sheet, right? The space where the field theory lives is just a two-dimensional space. Okay? It's an R1, 1 space. And these x's are scalars in that space. Now, I could also say that these x's transform like vectors. In what space? So that would be in the internal space. From this point of view, these indices would be indices of the internal space. Okay? But that's what we're going to call the target space. Okay, so these indices refer to the target space. Okay, very good. So last time, we also wrote down the equations of motion, and we said that we got something like I think we also decided to introduce a little bit of notation and said that perhaps it was easier to write a dot. Now this is a scalar product, right? Here we are dotting the target space indices, okay? So we have to remember what this dot means, because soon there will also be another dot that we're going to put here, and that dot would mean derivative with respect to the world sheet time. Okay? And the equation of motion was that these have to vanish. Okay? So one exercise that you guys had, which I believe you did during the tutorial, was to integrate out the metric h. So let me just do it quickly. In order to integrate out the metric, a trick is the following. You can just realize that this object is already sitting here. Okay? So you could say, well, let's use equations of motion. And realize that everything here depends on the metric, but nothing here depends on the metric. So this would be a nice object to use in order to integrate out the metric from here. How can we do that? Well, you see that there is a determinant of the metric here, and there is a metric sitting here. So if we just take the determinant, we will get something that looks very similar to that. So let's take the determinant of this formula. So let's give a name to this. Let's call it G alpha beta. And so when we compute the determinant here, we get 1/2 this factor square, and we get the determinant of this. Okay? But now we see that we want minus the determinant of this because we are in Lorentzian signature. So we should have started with minus, and we put a minus here. Now we can take the square root and find exactly what we wanted. This whole factor here appears on this side, and it's just given by this formula. That means that the effective action for x after integrating out h is given by minus the integral d2 sigma square root of square root of the determinant of G alpha beta. Sorry, minus. Okay. Yes. What is positive?
When you check the square root.
Well, we know that this is equal to that. Well, once again, now we're going to interpret what this is, right? So this G alpha beta as an interpretation, right? So if we start with our space R1, 1, and we think about the x's as being a map that is taking this two-dimensional object into some d minus 1, 1 dimensional space-time. So this thing, or the x's, are mapping this two-dimensional object into some two-dimensional space here. And we can give an interpretation to what this is. Okay? This is just the induced metric here from the metric in the space-time. So what we are really computing, by computing this determinant, is just a little bit of the Lorentzian area of this object spanning space-time. That's how we know that locally it will have to be negative. That's why we have to put the minus sign.
I mean, on the right-hand side, you remove the square.
On the right-hand side, well, from this equation, we could also know that, right? This is already square. So this thing has to be negative because we know that there is this minus sign. But that also comes intuitively from the embedding of this space into this space.
How did we get this in square?
How did we get what?
In second row, why do we have this square?
Oh, why do we have this square? Does anybody know why do we have this square there? Oh, that's very important. Excellent. Remember, this is a number. So we have a matrix H 0, 0, H10, H01, H11 times this object. Let's call it A times A. We're computing the determinant of this. right? So you get A squared times the determinant of this matrix. Okay, very good. Now, if we really want to think about the x's as being a space-time, so they carry dimensions, right? Dimensions of length in a space-time, or in this target space. And therefore, this would be computing an area. But we don't want an action that has units of area, right? So we have to compensate with that, for that fact. And the way to compensate for that is to introduce a dimensionful parameter that we're going to call t. And later on, we will interpret as the tension of the string. At the moment, there is no string here. This is just a two-dimensional object that we're mapping into this space. It's an infinite dimensional object. But later on, if we have time, and we make a connection to the Veneziano amplitude, we will see that in order to get the Veneziano amplitude, the way he wrote it down, we will have to define t to be 1 over 2 pi alpha prime. Alpha prime has dimensions of length squared, okay? Because t should have dimensions of 1 over area in order to make this action dimensionless. But since we know where we want to go, right? Remember, we're doing all this because we want to describe these relativistic strings that are supposed to describe the strong interactions. So having something that is infinite, that covers the full r,1, will give us something that is infinite here, too. So we have to do something about that. We don't want something like that because we don't see infinite one-dimensional objects propagating in space-time, right? Remember, what we want to do at this point is to model the hadrons as little strings. So how can we do that? Well, one way to do it is to restrict the region of integration here so that on this picture, we get something that has finite length. We could try to do it and then see if we succeed in getting something that makes sense. So the proposal I'm going to make is to restrict the sigma domain to be from 0 to pi. Once we do that, the image of this strip in a space-time will no longer be something infinite. To know what it is, well, first we have to map the boundaries and see what they look like. Say one of the boundaries goes like this, and the other boundary maps to something like this. Then we map the interior. And that will definitely look like our nice little string that is supposed to describe one of the mesons. Very good. But we could also have done something else. Perhaps we could have identified this boundary with this boundary in a space in the target space, so they would correspond to the same line. And if we did that, then the object we will be describing would look like a tube. So one of them will be an open string, or what we would call an open string, and the other one will be closed. Okay. Very good. Of course, just like in the one-dimensional case when we studied the string, we said, well, nobody stops us from making this more general, right? So we could have replaced this by a general metric in a space-time that depends on x. And if we did that, then all the formalism we have done would describe the evolution of a string moving in a curved space-time. Okay? Now, from the point of view of the field theory living on the wall sheet, this is not a metric in any space-time. This is just a complicated way of writing a coupling between the scalar fields. That would be such a nightmare, right, to have something here that depends on x, but that would just be a quantum field theory in 2 dimensions, okay? So in principle, we could do it and live with that. So it would just be the most general coupling that you can have of the scalar fields with themselves. But in space-time, we will have a completely different interpretation of what's going to happen, of what is happening. Okay, very good. Now this action is what is called the Nambu-Goto action. And in fact, it's the first action that was written down, just generalizing the point particle action. It's the first thing that you will write down if you were looking for a theory of strings. You would write, instead of generalizing, instead of talking about the proper length, you would talk about the proper area, and you will write an action so that the equations of motions would be giving you something that extremizes the proper area of the object propagating in space-time. Very good. The reason we don't discuss this very much is that just like in the one-dimensional case, introducing this auxiliary field or introducing this new field makes equations of motion much, much simpler and the theory much easier to quantize. So we're going to be working with that. So let's do that. So we're going back to the Polyakov action. Back to Polyakov and to our flat space-time metric. And let's study the properties of the action. So this action has the general properties we discussed yesterday. It's invariant under diffeomorphisms, which are nothing but general change of variables of coordinates. Okay. We can write it as sigma and tau if we want. It has global symmetries. But it also has something new. I asked you to find out what the new thing was. Is what? You should all be experts on that, right? Because you took a full course on conformal field theory. And this should be the first thing you probably saw in 2 dimensions. Whenever you see an energy momentum tensor that is traceless, you say, yeah, this is great, right? I can go and use everything that I learned about conformal field theories. So there is Weyl invariance, and that means that we can take our metric and rescale it. Now, the diffeos give us the freedom to set 2 functions to anything we like in the metric. Now, the Weyl invariance gives us the freedom to set 1 function. But that's very interesting because we know that in 2 dimensions, our metric which is a symmetric tensor, has only 3 independent components. These 2 must be equal to each other. So we only have 3 independent components. So using Weyl plus diffeomorphisms, we should be able to gauge fix the metric to be something very, very simple. And the simplest thing that we can choose is to be the Minkowski metric on the wall sheet. Okay? Now, having done that, you would appreciate why we like very much the Polyakov action, right? Because after gauge fixing, the Polyakov action will look very, very simple. Well, let me put back the T, okay, the tension we decided to introduce. So what do I get? Well, here I want to introduce a notation. I think we did it yesterday, but just in case, let's repeat it. So we're going to denote by dot derivative with respect to time and by prime derivative with respect to sigma. So if we do that, what we get is x prime square minus, x dot square minus x prime square. So that's a very, very compact notation. Just for fun, let's write what this means explicitly. So this square, well, first of all, the dot means derivative with respect to time. This square means contraction with the space-time or the target space metric. Okay? So that's what this means. Likewise, derivative with respect to sigma are denoted by prime, so we get the same object on that side. All right, very good. So now let's study the equations of motion, or the field equations. So let's vary our action. Our field is x, so we can vary the action to get something that looks like 2 times okay. That's very simple. Now we integrate by parts in order to get rid of the derivative with respect to time and the derivative with respect to space on the wall sheet. So we get, let's cancel these 2's with the half that we had here. Okay? So we get something that looks like x. So when we integrate by parts, we will pass one derivative to this guy, and it becomes a double dot, delta x with a minus. But we also pay the price of a total derivative with respect to time of this object. On this side, we get something that looks like x double prime delta of x minus derivative with respect to sigma of x prime delta of x. Okay? From there, we can read immediately what the equations of motions are, because we get something that looks like this. Double prime, thank you. And we get the 2 boundary terms. Now, we will worry about the boundary terms later, but certainly we want to make them 0. So at some point that will happen. But for the time being, let's worry about this. Since this must be 0 for any genetic variation, we conclude that x double prime minus x double dot x double prime must be 0. Okay? For every component, for every scalar field that we have on the wall sheet, this must be true. So let's write it more explicitly in equations. So the second derivative with respect to time and the second derivative with respect to space direction of all the scalar fields must vanish. Okay? So this is our equations of motion. That's very good. Of course, we have to remember, just like in the one-dimensional case, that gauge fixing didn't come for free. We cannot just pretend that this is all we have to do. We also have to impose a constraint that comes from gauge fixing. And the constraints come from imposing the equations of motions with respect to h at all times. So the equations of motion are, well, they were somewhere there. Well, those are the equations of motion, right? On the top. So let's see what they are. So we have to impose that every component vanishes. So what is a 0, 0 component? Well, let's look up there. The 0, 0 component looks like x dot squared, right? Remember that the right-hand side on the top equation up there, the right-hand side was on the left-hand side at the beginning with a minus sign. So let's keep it there because we're computing t 0, 0. So you have minus a half. We're looking at the 0, 0 component, right? So the 0, 0 component gives us a minus sign. So there will be a plus sign here. And then we have to write down the object that multiplies the metric. And that thing would be minus x dot prime plus, x dot square, x prime square. Well, this is nothing but a half of x dot square plus x prime square. So we have to impose that this is equal to 0 at all times. Now, you have to check that t0, 0 is equal to t11, okay? Just from the equations there. So that doesn't impose a new constraint. Just by setting this equal to 0, we are setting this equal to 0. And the final constraint is t01, which also happens to be equal to t10. And it's very easy to read from there because in this metric, the second term vanishes and only the first term contributes. So we get x prime dot x dot. And this also has to be 0. So the constraints end up being, we have to impose this, and we have to impose that x prime dot x dot is equal to 0, and that x prime is x dot square plus x prime square is equal to 0. Okay? These three equations should give us all the information we need. Of course, not yet, because I haven't told you what to do with the boundary conditions. So we have to do something with the boundary conditions in order to make these terms vanish. So let's discuss the boundary conditions. Well, first of all, we're going to assume that we have something that looks like x dot delta x. This is the first one. So we're going to assume that these variations are actually dying off at infinity in time. So at minus infinity and plus infinity, we're going to assume that these variations vanish fast enough. So this is actually 0 by assumption. So we don't have to worry about this. But now our space, or the spatial direction, is compact. So we cannot do the same thing that we did here, or that we usually do in quantum field theory, where we assume that fields or that the variations vanish fast enough at infinity. Here, this is compact, so we don't have that possibility. Instead, we have to worry about what they are. In other words, we have to set this quantity to 0. So we have to find ways of setting this to 0. Yes.
Why in the equation do you have 2?
Sorry?
Why in the second equation, why do you have 2 between x prime and z prime?
This dot?
Yeah.
Well, let's write it explicitly. What is this? This is derivative with respect to tau, to sigma, sorry, of x mu delta x nu eta mu nu.
Because initially when you wrote it without it.
Well, because I was lazy, yes. You should say, yeah. Yeah, so that would have been a good question. Why don't you have a dot there? Excellent, yeah, very good. In fact, here. Yes.
Why did you say the first one was the first?
Well, in quantum field theory, we do that also. We say that when we do variational analysis, we usually assume that any fields that we have vanish, any variations that we have vanish at infinity. So that's a variational principle that we usually use.
It's not that we keep it at a fix from the beginning of the.
Well, what I'm saying is that the variation vanishes at infinity. Okay? So if you wish, yeah, we say that there is some boundary condition at minus infinity and plus infinity. Some asymptotic states that were fixed. Okay, so what are the ways we can set this to 0? Well, 2.1 could be, one possibility is to set x prime of the mu component for any tau at sigma equals to pi. We could set this to 0. That would be a way of getting rid of the first term. Well, of course, if we do it for this one, we could also do it for the other one. And or x prime mu for any tau at 0. We can set it to 0. Now, these kind of boundary conditions are called Neumann. We have another possibility. We could say that x mu for any tau at pi, at sigma equals to pi, is in fact a constant. It's just a fixed number. So if it's a fixed number, it means that the variation vanishes. So we're setting this to 0. So by choosing this boundary condition, we're setting the variation to 0, not the derivative to 0. So we could do it here and or at 0. Okay? And these are called Dirichlet. Yes.
Does it matter we define sigma to go from 0 to pi?
No, it's just a convention.
Right. So,
As long as it's compact, it's
Yeah.
just convention.
okay, so why did they choose pi? Why not 2 pi?
If we had chosen 2 pi, you would ask, why not pi? And
Right. Okay.
it's the same answer, exactly. Well, but there is also 2.3. What could 2.3 be?
Why should we put 4?
Oh, because really what I should say maybe comma. What I mean is that we can choose any combination of this. Say you can choose this and this. You can choose this and this. You can choose this and this. Any combination you like. As long as that thing vanishes, you can choose any combination you like.
But not vertical.
Very good. Not vertical, indeed. I have to be very precise here. Okay, but there is a third possibility. What is the third possibility?
Some divided and some new ones.
Sorry?
Some dimensions with one and some dimensions for the other.
Yeah, of course, we can do this independently for each dimension. That's true. But there is still another possibility that we can choose. Where?
That's going to be equal.
Make sigma periodic?
Yeah, we can make them periodic.
Oh, right.
So we can choose so this is what is going to give rise to closed strings, and these ones would be open strings. Okay. So you should start thinking, because I need, let's see what time, I'll need 3 volunteers. Okay? So start thinking if you want to volunteer. So let's put this up a little bit so you can see. Okay. So why do I need volunteers? Well, because I figured it would take me too long to do it myself. But it would be nice to actually do it. So let's play a little bit with the boundary conditions. So imagine, let's just play a little bit. So imagine that D was actually equal to 4. Okay? No reason whatsoever. It means that we have a space-time, or a target space, which is R3, 1. So the good thing about this is that we can actually draw it, at least the space part. So let's imagine that we have an open string. And now we're going to introduce the following notation. We're going to say what happens at sigma 0 and what happens at sigma pi equals to pi. And let's draw our 3 dimensions, x1, x2, and x3. Sorry, let's do x2 and x3. We're not going to worry about time. Okay, so we have this. And then we're going to specify the boundary condition for x1, x2, and x3 at these values of 0 and pi. Okay? So I'll do the first one. I'll assume that I have Neumann boundary conditions here, 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 and here. Okay? So that's the one I'm going to do. Well, what does this look like? remember, this is going to be a snapshot of the object because we're not drawing time. This is just at a fixed time. So how would it look like? Well, it just looks like a string moving freely there where the endpoints are not restricted to be anywhere in particular. Okay? So this would just be an open string where the endpoints can move freely in our whole space-time. All right. But what if I try to do something more interesting? Something like, let's say that here I have a Dirichlet boundary condition. And I also have it here. Okay? But then I say that, well, no, let's just do one here. I have Dirichlet boundary conditions here. But in order to give you, to specify the boundary condition, I have to give you what the value is, right? I have to tell you what this is. So I'm going to tell you that this is Dirichlet, and the value that we're going to put is, say, 1. So x1, 0 would be 1. So I look here for 1, the point 1, and I have to draw this open string. So what would it look like? Yeah, you know, I just realized that it would be a little bit hard to draw it like this. So maybe I'll move my boundary condition here. And I'll put Neumann here. Okay, so it's here, 1, not here. So one of the end of the strings is free to do whatever it wants. The other one has a Dirichlet boundary condition in the x2 direction. So that means that I have to draw the plane x2 equals to 1. So this is a plane x2 equals to 1. And my string, the end sigma equals to 0, is restricted to lie on this plane. It cannot wander off this plane. It has to stay on this plane. The other end can do whatever it wants. Okay? So have you thought about who wants to be a volunteer? Any 3? Okay, 1. That's great. 2. And 3. Okay, excellent. So, and perhaps I need some help from the tutors just to make sure that. So I want one of you to be drawing on this blackboard, and perhaps, well, 2 of you drawing here, and 1 over there. And here are the boundary conditions I want you to draw. It's just that I figured it would be nice to have many examples of this, but it would take too long for me to do all of them. So here it is. So we can have Dirichlet boundary conditions, Neumann here at -1, say, and here Neumann, Dirichlet at -1, Neumann, Neumann. The next one will look like so Dirichlet, this is 1, x1, x2, and x3. Here, Dirichlet at 0, Neumann, Neumann, Dirichlet at +1, Neumann, Neumann, and the last one would be Dirichlet at 0, 0, Dirichlet -1, Dirichlet -1, Dirichlet 1, Dirichlet 1. Okay? Well, maybe And I don't remember your name.
Ali.
Ali?
Allah.
Is that? OK. So the reason I need help from the tutors is just that to make sure that each of them is yeah, you can go there. Yes, very good. Of course, everybody else should also try to do it, right? It's not like they will just do it on the blackboards. But I also want everybody to try.
Actually, it has to do with oh, but it has to be complete.
OK, excellent. So let's start with Ali. So you already finished. So we have Dirichlet on 2 at -1. So -1 is somewhere here. There is a plane. Both ends of the strings are supposed to land on the same plane. So they are restricted to be there. And the string moves around. That's very good. OK? Excellent. Now, note that there is something interesting here. Since the strings have tension, right, the string somehow wants to be close to this plane because both of these ends are on the same plane, right? Now, from the point of view of the plane, these points look like particles. So you say, well, in string theory, we have strings. But look, if you were somebody who lives on this plane, you would think that these endpoints are particles. In fact, they could even be charged. So people at the beginning, they thought that these boundary conditions were unphysical. And the reason is that, well, if you wanted to have a space-time with some dimension, something like this will clearly break one of the symmetries we had. What symmetry would be broken?
Translation.
Yes, that's right. So Poincaré will be broken. But now imagine that for some reason, any resemblance with real life would just be an accident. For some reason, we end up finding that the dimension that is chosen by the string theory happens to be 26 and not 4, or 10 and not 4. Okay? Then imagine that in our 10 dimensions or in our 26 dimensions, there is some boundary condition that we can impose so that the strings or the endpoints of the string only live in a 4-dimensional subspace or a 3+1 dimensional subspace. Well, who knows? Maybe we live on that 3-dimensional subspace, in 3-space-dimensional subspace, and +1 will be time. So people later on realized that, in fact, the consistency of the theory requires the existence of other objects that are not strings. Yes?
What if we have the boundary conditions that the endpoints of the string is on the surface, but also intersections of the string? Do we have then?
What do you mean intersection? That parts of these would also be here?
Intersects again several times with a plane, and we would get several particles just of one string.
Well, you see, the string can certainly break into different pieces, right? So you can have something that looks like this, and these 3 points are on the plane, right? But you would interpret these as 2 strings that are interacting. Remember, the boundary conditions, we could only impose the boundary conditions on the endpoints. The rest, we didn't have any choice. Only the equations of motion will tell us what they do.
Okay.
Right? So this object, as it looks like here, is a 2-dimensional object, right? So this is something that we call a 2-brane. The 2 refers to the number of space directions of the object. Okay? The reason is that time, everything has time, so let's not worry about time. So in general, if the string, the endpoints of the string are restricted to live on a p-dimensional object, on a p-space dimensional object, of course time is there, we call that a p-brane. Okay? So in this case, we have a 2-brane. And as I said, in the hypothetical case, that the strings will end up living, say, in 10 dimensions, we can have a 3-brane, and perhaps we live on this 3-brane. Now, there is something interesting, right? If the theory also has closed strings, right? The closed strings, we saw the boundary conditions. So the closed strings somehow will not be restricted to live on this brane. The closed strings will be free to live everywhere else. And as somebody reminded us yesterday, I think it was you, what's your name? Aitor. So I think Aitor told us yesterday that, well, if you have open strings, you don't have gravity by itself, just in the spectrum. But the open strings can interact and produce closed strings. Then the closed strings will have gravity. Okay? So somehow gravity will behave very differently from the other fields that live on the 3-brane. Is that good or bad? Well, it depends. Because it means that if you live on the 3-brane, if you're restricted to live there and gravity lives anywhere else, then the scale at which the 2 things interact will be very, very different from the point of view of the brane. So it would mean that forces on the brane that are carried by the open strings will look much, much stronger than gravity. But is that something we like or that we don't like? What do you think? Is gravity very strong? What do you think? No. It's actually incredibly weak. That's actually one of the $1 million questions, right? The hierarchy problem. Why is gravity so weak compared to the other forces? Right? Well, now you can tell why people got excited when this possibility was open. It could be a natural explanation for the hierarchy problem. And you will probably see it in beyond the standard model. Yes?
And so in this picture, if you have strings with open strings with all Neumann,
or if you have
all Neumann conditions, and how would they look when they intersect the brane?
Well, they could do. It depends on the theory. So
you can have that.
So those details would depend. Yes, you could also have that. Yes. Okay, so let's go back here. Now, I think this was Dalimil, right? No, you did it there. No, this was you, right? Yeah. So, what would this be called? A what? So there we had a plane.
Yeah.
Here we have what, a point. So how would this be called? A 0-brane. Okay? So a string theory also has particles. They are called 0-branes. Okay? And here we got something very complicated. Well, I think this can only be called intersecting branes. Okay? Hopefully, it might be too ambitious, but perhaps we will see at the end of the course a way of getting the standard model from intersecting branes. Okay? All right. So let's now continue. what do we want to do? Well, we have the equations of motion. We want to solve them. So that's the next step. We want to solve these equations of motion. Well, somehow it doesn't get any easier than this. Well, in fact, it even gets easier if we find the correct variables to solve these equations. So let's use Lycon gauge, Lycon coordinates. We introduce sigma plus minus to be a half tau plus minus sigma. If we do that, this becomes, I believe, this is equal to, well, maybe we can put plus. And then our equations, our field equations, are very simple. They simply look like derivative with respect to sigma plus, derivative with respect to sigma minus of x mu equal to 0.
A question?
Yes.
Wouldn't it be, okay, usually you also have a factor of half, but you're not worried about that.
Yeah, I'm not worried about factors of half. That makes you happy, then let's put the factor. Yes. Yeah, I'm not worried about the factor of half because we're just solving the equations. It's equal to 0.
Actually, isn't it a factor of 2?
I told you, I'm not going to worry about that. Completely irrelevant for the equations of motion. Okay, so what's the most general solution to these equations? Well, whenever we see an equation like this, we know that it separates into two for reasons we will explain later. It separates into, well, they are called right and left-handed. So right movers and left movers. But for the moment, it's just notation. Let's call these ones R and these ones L. Okay. So if we have a function that only depends on sigma minus, the derivative with respect to sigma plus will kill it. And if we have a function that only depends on sigma plus, the derivative with respect to sigma minus will kill it. Okay. Now, of course, we cannot solve these equations unless we know the boundary conditions. So let's choose some boundary conditions. I'm going to choose the closed boundary condition, the closed string boundary condition. Okay? So remember, the boundary condition is that x mu of tau sigma, now in the all variables, is equal to tau and sigma plus pi. So the whole string is periodic. So I want to solve these equations assuming that boundary condition. Well, how can I do it? Well, something interesting is the following. If you notice, and I take, so I'm going to be lazy. I'm going to denote this derivative as del plus and this derivative as del minus. Okay? So if you take del minus of x mu, we get del minus of x mu r, right? Because we killed the second part. And if we take del plus of x mu, we get del plus of x mu left. Now you see that independently, they don't have to be periodic, right? Because nobody's telling us that the left part and the right part will have to be periodic in sigma. It's only the sum that has to be periodic in sigma. That's the boundary condition. But once we take the derivative, we kill one part or the other, and therefore, this whole thing will be periodic. So this whole thing will be periodic in sigma, and this one will also be periodic in sigma. So we are in business because we have a periodic function in sigma, and we can expand it in Fourier modes. So let's do that. So let's take this and expand it in Fourier modes. So what are we going to have? We're going to have an expansion in Fourier modes. Remember, this only depends on sigma minus. Okay. Now, here is perhaps where your complaint about the choice of pi and 2 pi will come. We chose pi, right? And we want something that is periodic with period pi. So we're going to pay the price of not choosing 2 pi and so on. So we will have to put a 2 here, right? Because this sigma is tau minus sigma. This sigma minus is tau minus sigma. So if we want this function to be periodic in sigma with period pi, we will have to put a 2 here. And I agree, that 2 looks a little bit ugly there, but we had to make a choice. Now, the coefficients are usually called alpha. And of course, they have to be different for each of the scalar fields. In other words, they have to be different for each of the indices mu. Okay? And we have 1 per Fourier mode. Now, remember, we want this to have dimensions of length in space-time. And it will be convenient to have the Fourier modes to be dimensionless. So let's put here some length, which we're going to call the string length. All right. Now we can do the same thing for the left movers. And here is where I don't quite remember what's the usual convention, because we can definitely allow different modes for the left movers, and one of the two is called alpha tilde. And I think it would be great to have the standard conventions. That's the reason I wrote it here. Somewhere. Yep, but that's correct. Okay, but we're not after these guys. What we're after is the full formula for x mu. Okay? Well, we need this x mu r and x mu left, so why don't we integrate these equations? So let's integrate the equation. Of course, integrating this equation will allow us a constant, which we can call it little x mu r, plus integrating this is very easy, but we have to be careful with m equals to 0, right? M equals to 0 is special. So if you have m equals to 0, we get ls alpha 0 mu times sigma minus. That's what we get. And the rest will be something like so here I want to be careful about the factors. So if we want to get this if we take a derivative. So we will need something here like minus 2i. Or if we want a plus, yeah. So that would be correct, right? No, it would be plus here. Sorry, what am I saying? It would be a half. All right, excellent. So we do the same thing for the left movers. So we will get from the 0 mode sigma plus I. We will have alpha tilde. For m different from 0. Okay. Now, are we done? Well, not yet, because this is what we want. And by adding these two things, we still get something funny, slightly funny. Can anyone see why we cannot just leave this like this? There is something that we have to fix.
It's not completely periodic.
Very good. It's not periodic. It's not properly periodic in sigma. And what do we have to do to fix it?
Set the two alpha zeros equal to itself, to each other.
Very good. We do that, and then we're in business. So the problem is that we want this to be periodic in sigma. So everything here is periodic in sigma. But if we look here, we're in trouble. And the reason is that we're going to get the sigma dependence of this. Or in other words, this will be something that looks like tau plus sigma, or actually the minus here. Okay? So this piece is not periodic in sigma unless we set this to 0. So the final solution is what we have here, but setting this to 0, which implies that this has to be equal to this. Okay? And once we do that, we can simplify this factor and get a factor of 2 and put it here. Okay? So let's clean this up a little bit, and let's actually do it and put it there. It will be 2 tau alpha nu. And that's our solution.
Do we have an issue with this maybe not being real? Because if we want our derivatives to be real, that means that alphas have to pair up, plus and minus m have to be the same.
Excellent. So our x better be real, and therefore we need a relation of this form. Sorry. All we need is something like this, right? At this point, we can just say conjugate. And start. Very good. Now we have the full solution, and we're all happy, and we can end for today. Well, maybe not quite. You should do something. Now, here is what you have to do. I want you to show that if you solve the field equations using Neumann boundary conditions, you get the following. So if you use Neumann, in other words, you're going to be doing the open string. Show that you get something that looks like this. Now it's the end. So this is an exercise.